Good day, it's your man Chiefs again. How are you doing? Hope you're all well and getting ready for the final exams. Today, I'm looking at photoelectric effect, all right? Photoelectric effect, what is it all about? Well, think of an incoming radiation. And an incoming radiation, what does it do? It gets onto a metal, and inside the metal, there is a sea of electrons waiting to be set free. And what happens when that radiation comes in contact with the metal? Some of the electrons are released or are knocked out. Okay? That in itself is photoelectric effect. Photoelectric effect is the process by which electrons or an electron is emitted by a substance when light shines on it. So we are coming from the premises that says if light is shined onto a metal or onto a substance is able to emit electrons. Okay? But not every light does that. We have to talk about wake function before we go further. There is a minimum energy required to knock off an electron out of a metal. This minimum energy is called the wake function. The wake function is given symbol WO. As much as we've got the minimum energy required to knock off an electron, we also have a minimum frequency, because remember, light has got a frequency. The minimum frequency required to knock off an electron is called the frequency threshold or threshold frequency. The minimum amount of frequency required to knock off an electron from a metal is the threshold frequency. All right? Let's look at a few formulas that are applicable with or to photoelectric effect. The first one, which I talked about when we looked at Doppler effect, is the one that says E is equal to HF, which is equal to H multiplied by C over lambda. Now you might ask, where does the C and the lambda come from, right? While the speed of sound is generally given the symbol V, all right, in air, the speed of light is given the symbol C. So when you have a situation where we are talking about the equation that we used before, where V was equal to F lambda, if we have C is equal to F lambda, where we consider C as the speed of light, because light occurs or behaves as a wave as well as a particle also, all right, where it has photons of energy. All right? So V can be substituted with C, where C becomes the speed of light is equal to frequency of that light times the wavelength of that particular light. Okay? So the energy is equal to HF, where H is Planck's constant from our understanding H is equal to 6,63 times 10 to the power negative 34 joule seconds. Okay? So, if we do not have the value of F, and we've got the value of C and lambda, we can conversely say that C over lambda gives us the value of F. So that's where this one comes from, all right? Now, in a situation where the energy, all right, that is given onto a surface is greater than the work function, which we now know work function is as a result of H multiplied by FO. It is an energy where F0 represents the threshold frequency and W0 represents the minimum amount of energy required to eject an electron from the surface of a metal. Then if E is greater than WO, the ejected electron will have a kinetic energy. I think that makes sense. Playing around with that equation tells us that EK max, all right, is going to be equal to HF, all right, minus WO, all right, of which HF here is representing the E. Let's look at a quick example here. The quick example says light of a certain frequency is shown onto a metal M, all right? Let's call that frequency X. Okay, try to use a different color there. Let's call that light frequency X. Is shown onto a metal and M, and electrons are ejected off the surface. The same light is shown onto another metal N, okay? The electrons ejected from the surface of N have much higher kinetic energy than metal M. All right? This means that, what do you think? So if they've got a higher kinetic energy, it means that the WO plus EK max for this one is greater, okay? So what does that tell us about N's WO? It tells us that N's WO, let's call it WON, is less than M's WO. Sorry. Very sensitive board. All right, so let's look at the answer. Metal N has the same wake function as metal M? No, it can't be the same, because if it had the same, the EK max would have been equal. Metal N has a larger work function than metal M. No, the threshold frequency of metal N is higher than that of metal N. No, because if we were talking about threshold frequency, is directly proportional to E, as you can see from our equation, the one that we showed you before, that says EWO, is equal to H times FO. Okay, so those two are, if we consider that the Planck's constant is the constant in this instance, W and WR and FO are directly proportional. Okay, good. So we are saying in this instance, if WO is directly proportional to FO, and we agree that WON is less than WOM, it would mean that the FO of N is going to be less than the FO of N. So what is the answer there? The threshold frequency of N is lower than that of M. All right, there is our correct answer. Very simple question there. Okay, one of the things that maybe people brush aside within the teaching of physical sciences to grade 12 is the electron volts. Okay, 1 electron volt is equal to 1,6 times 10 to the power negative 19 coulombs times 1 volt. Okay, that's an electron volt. And an electron volt is energy. It's 1,6 times 10 to the power negative 19 joules. Hence, 1 electron volt is equal to 1,6 times 10 to the power negative 19 joules, which means 1 joule is equal to 6,241 times 10 to the power of 18 electron volts. Okay, so remember that in the scheme of things, it comes very handy when you're then applying it in calculations that are involving a situation where you got an electrovoltaic cell. What does an electrovoltaic cell do? It provides light, and from that light we produce electrons, and we produce a flow of electrons, which is current. Okay, this number you already know. Think of it as E, charge of an electron, times 1. This value you can then find it conversely, all right, by dividing. Okay, 1 into 1 divided by 1,6 times 10 to the power of negative 19. Okay, having said that, we move on to electron, the continuous spectra, the absorption spectra, and emission spectra. These aspects are very important. Continuous spectra is the spectra obtained from light passing through a prism. Which light? White light. So when light passes through a prism, it produces the normal continuous spectrum. But when light is showing an absorption spectrum, okay, this is when radiation, electromagnetic radiation, is being absorbed by atoms, ions, or molecule, and we produce what we call the absorption spectrum. The opposite of the absorption or inverse of absorption spectrum is the emission spectrum, obtained by emission of electromagnetic radiation to the atoms, ions, or molecules of a sample of mass. Okay, now, here is a question. Elena writes the following statements about emission spectrum of light. All right, I gave this question so that we can be clear on what emission spectrum is. An emission spectrum is formed when a certain frequencies of electromagnetic radiation passes through cold gas. This one is incorrect. The lines in the emission spectrum of an atom have the same frequency as the corresponding lines in the atom's absorption spectrum. This one is correct. An emission spectrum is formed when the atoms make transition from a higher energy state to a lower energy state. This is correct. With the absorption spectrum, it's the other way around. It is when atoms make transition from a lower energy state to a higher energy state, right? So which one of the following is correct? Our correct answer there for that particular question will be D. Okay, not D, sorry. 2 and 3, that will be C. Good. Okay. Now, there is a question from 2018. And this question is saying, all right, you are given 2 different metals. The threshold frequencies of calcium and potassium are given in the table below. All right, and there are 2 different values there. The first value is for calcium, 5,07 times 10 to the power of 14 hertz. And the next one is for potassium, 5,55 times 10 to the power of 14 hertz. It says define the term work function. You must be ready to give a definition of such words like work function. Work function is given as, of a metal, well, is given as the minimum amount of energy that is required to eject electrons from the surface of the metal. All right, so that's the work function. We've already talked about it there when we looked at the F0 and the equation. The minimum amount of energy required to eject electrons from the surface of the metal. The question then says, which one of the 2 metals in the table is the higher work function? All right? Give a reason for the answer to the question. All right, so this one, potassium, is 5,5 times 10 to the power 14. Calcium is 5,07 times 10 to the power 14. Which one is bigger? Okay, which one has got a bigger F0? This one has got a bigger F0. FO of potassium is greater. Potassium is K, by the way. Let me put it as FO of potassium is greater, okay, than the other one, all right? So, the reason for our answer is if FO is greater, okay, FO is directly proportional to work function, all right? So our answer there is potassium. Good. All right, having said that, let's move on to the next part. Is that the next question? Yes, it is. All right, so the next question says, I'll read it from here because it's not clear from the board. It then says that the simplified diagram below shows 2 circuits, A and B, containing photocells. Photocell in circuit A contains calcium and metal plates, while photocell in B contains a potassium metal plate. Okay? Right, so here's a diagram. We got cells, all right? We spoke about photocells before, giving light and producing a current. All right, so this is calcium, and here we got one with potassium. Ultraviolet light with the same intensity and wavelength of 5,5 times 10 to the power negative 7 meters is incident on the metal plate. In each of the photocells, all right, and the ammeter in A registers a current. Ammeter in A registers a current. By means of calculation, determine whether the ammeter in B will also register a current. So what calculations do you think they want us to find here? All right? What calculation do you think they want us to come up with? All right. If in the question they've just given us the wavelength, okay, and previously we were given the frequency, threshold frequency of the two different parts. All right. So what they want you to calculate here is they obviously want you to calculate the frequency of the UV light. Okay. What is the frequency of that UV light? This is 11.4. How do we come up with frequency? Okay, when we are given the value of the wavelength. To find the frequency, we know that speed of light c is equal to f multiplied by lambda. Okay, our understanding is that frequency is equal to c over lambda. Okay, the speed of light, we must know, is 3 times 10 to the power of 6, which is 3 million meters per second, divided by the lambda in this instance is 5,5 times, this is the frequency of UV, okay, times 10 to the power negative 7. All right. Our calculations will show us that the frequency is 5,45 multiplied by 10 to the power of 14 hertz. 5,45 Okay, if we are going to compare 5,45 to 5,55, this frequency is less than that frequency. So, which means therefore that there will be no emission of electrons in circuit B. All right. So threshold frequency of potassium is less than threshold of frequency of potassium is less than the amount of frequency of the UV. In other words, we can put there no emission because F of UV is less than F0 of potassium. Okay, so that answers the question here for 1.13. 1.14 then says calculate the maximum kinetic energy of an ejected electron in A. What do we already know? We know that from our formulas, in order for us to calculate the energy, it's equal to work function plus EK max. All right? So the question requires us to find the maximum kinetic energy of the ejected electron. How are we going to come up with the maximum kinetic energy of the ejected electron? Okay, so for the energy of the electron, it is simply going to be equal to H multiplied by C over lambda, okay? H multiplied by C over lambda. So our H multiplied by C over lambda is equal to work function is H, all right, multiplied by frequency O, right, over lambda plus the value of EK max. All right. So if we substitute those values, we find out that we have our energy of the light that's being produced or that's being given, which is the energy of the UV light. Maybe you might need to mention that here, being, we use the Planck's constant, which we mentioned the Planck's constant is equivalent to 6,63 times 10 to the power negative 34 divided by the value of lambda, which is the wavelength, 5,5 times 10 to the power negative 7, all right, multiplied by the speed of light, which we know is 3 times 10 to the power of 6, is equal to 6,63 times the value of FO, which is the frequency threshold of the potassium, the caesium in this instance. Okay, so frequency threshold of where we've got C times lambda O, all right? So times 10 to the power of negative 34, okay? Multiplied by 3 times 10 to the power of 6 divided by the value of lambda O. Where is our lambda O? 5, lambda O is substituted by 5,07 times 10 to the power of 14, which is the work function. So we remove that. The work function represents our lambda O. So in other words, here we can substitute that with FO. Okay? So I think it's the one that we are given in the table there. In the table, right? Yeah, 5,07 times 10 to the power of 14 hertz, right? And then this added to EK max. All right, so let's go through this. It's a bit of a lot of large numbers here, all right? Can be confusing. What we are saying is that the EUV, the energy of the UV, is equal to the work function of the caesium plus the EK max. Simple, all right? 6,67 times 10 to the power negative 34 times 3 times 10 to the power 6 divided by 5,5 times 10 to the power of negative 7, which is the wavelength okay, of the UV light is equal to 6,63, which is the value of H multiplied by 10 to the power of negative 34 times 5,07 times 10 to the power of 14 is added to EK. If you solve that, EK max is going to be equal to, try it on your own, attempt it on your own, find the value of EK. What is the value of EK there? All right, do your calculation. I'll try my own calculation here. It should give us 2,55 times 10 to the power of 2,55 times 10 to the power of negative 20, and because it's energy, the answer is in joules. All right. Good. Let's move on to the last part of this question. The last part of this question then says, how will the maximum kinetic energy of the ejected electrons calculated in question 11,4 change when the intensity of the incident light is increased? Okay. So if you look at the equation that's showing us what affects the EK, the equation E is equal to WO plus EK max. The only things that influence the EK max, which we know now that the EK max is equal to E minus WO, all right, is only the energy, all right, of the light source. And that energy is, as we now know, given by H times C over the lambda. Okay, so those are the only things, minus H times FO. All right, those are the only things that we can consider to influence. In this equation, there is nothing that shows anything to do with intensity. So we can increase the intensity to no matter how much we want to, but you must understand that nothing changes. So how will the maximum kinetic energy of the ejected electrons be? Maximum kinetic energy will remain the same. Okay, now, knowing for a fact that, just expanding this question a little bit, EK is equal to 2,55 times 10 to the power of negative 20. There are some questions that can ask you to find the velocity, okay? For you know that EK is equal to half mv squared. So in this instance, we can equate this to 2,55 times 10 to the power negative 20 and be able to find the velocity because we know the mass of an electron. Okay? Mass of an electron we must be aware of. All right. So that's just an extension of the question that you can come up with. Listen, this is part and parcel of what you should know for your paper one. I hope you've learned quite a bit and you'll be well prepared for your final exam. This is your main chiefs, and from me and the crew, it's ciao.